Okay, let's look at a technique called the trapezium rule. And what the trapezium rule does, essentially, if you imagine we had a curve, which was just a function of x, and we were trying to find the area between x0 and x3. So say, for example, if I wanted the area underneath this curve here. Now, obviously, we know that we can integrate to find this area. And if I integrate between the limits x0 and x3, that would give me the exact area between the x-axis on our curve. But sometimes there's some functions that are quite difficult to integrate, or maybe some functions that we can't integrate. So what the trapezium rule does essentially is it's a way of approximating this area. So like a key word to look out for in the exam is if it says approximation of an area, you know you're going to be using this technique. Okay, and just to visualize how the formula works before we look at the formula. If we were trying to approximate the area underneath the curve, we could split it up into a couple of strips. Now in this case, for my diagram, I'm just using 4 ordinates. The ordinates means just the x values. So if you think about it, if we were using 4 ordinates, that means we'd be using 3 strips. Because if you've got 1, 2, 3, 4 ordinates, there'd be 3 trapeziums, wouldn't there? 3 strips. Okay, and I'll try my best to draw on this. It might not be perfect, this, but essentially what we're doing is we're just approximating this area here as just as a trapezium. Okay, so if we think about how we find the area of a trapezium, we'd need the base. Now the base is what we call h in this topic, so the letter h essentially just stands for the width of each of our trapeziums. So each of the trapeziums would have a width of h, because we split it up into like even strips. So let's see, I'll draw it the other way around. If that was the trapezium that we're looking at, the width is what we call h. We need to get the parallel sides, these 2 sides here. And the way that we do that, if you think about it, if that's our x value, if we want to figure out the height of our trapezium, just sub it into our function. Like whatever this curve is, whatever this function is in the question, if I sub in my x value into my function, that's going to give me the y value, isn't it? So if and the notation, if that's x north, we'll call that bit y north. So that would be like the y value. And the other height here, x1, if we sub x1 into our function, that would be like the corresponding y value. And the way the area of a trapezium works, remember, is you add the 2 parallel sides together. You divide them by 2. So it's like an average of these 2 parallel sides. And then we multiply by the width. Okay? Now, obviously in the exam, you don't want to be messing about finding loads of different trapeziums. But just to give you a vague idea of like where this formula comes from, all that we're really doing when we apply this rule is we're splitting the area up into different trapeziums, and the y values are the heights of our parallel sides, and h is just the width of each of our trapeziums. Okay. One thing before we look at the formula, just one other thing to know, right? Imagine if we had this trapezium here as well, this red one. Right, so that red trapezium, that side there would still be y1, and that side there, if we sub x2 in, would be y2. So hopefully we can see these the middle parts, that height counts for 2 of the trapeziums, and that height counts for 2 of the trapeziums. The first one and the last one, we only need to count them once. So the first one and the last one only count for 1 of our trapeziums, but all the bits in the middle, we have to count twice. And if you can bear that in mind, you'll easily be able to see where this formula comes from that we'll look at now. Okay, so if we look at the formula, which we get on the formula sheet, it tells us the area is approximately equal to 1/2 of h, and the first and the last y values we only count once, and the y values in the middle, we have to multiply by 2, we count them twice. And just think about that, because these y values count for 2 of the trapeziums. But you know, as long as we know how to use the formula, that's all we need for this topic. H, don't forget, is essentially, h just stands for like how wide each trapezium is. But there's a calculation that we can do. It's like if you subtract your limits, so if you were trying to go between two limits, B and A just stand for the two limits, just remember that you divide by the number of strips. So in this first example, if we're going to be using 5 ordinates, we don't divide by 5. Okay, so if we look at this, let's look at example 1 and we'll see what I mean. So it says use the trapezium rule to approximate, on that word, we're looking out for approximation, the integral between 2 and 3 for ln of x. Do not integrate this, we want to approximate it. Okay, it tells us to use 5 ordinates. So the ln graph looks like this, just to try and visualize what's going on. We're approximating the area between 2 and 3. So if you think about it, if we're using 1, 2, 3, 4, 5 ordinates, there's going to be 1, 2, 3, 4 strips. Okay, so if you wanted to think about what h is, you could do 3 minus 2 divided by the number of strips, which is 4. And you can see that we're going up. In this question, h is just 0.25. So you're going up in 0.25s each time, and we're starting at 2, we're ending at 3. Okay. So a nice sort of quick way of doing this on the calculator, if you go onto menu, table, which is 7, type in your function. So our function, obviously the function that we're trying to integrate is ln of x, so I'm going to type in ln of x, and then press execute. Okay, so enter your function, and then you want to press set, which is F5. Start, end, and step. So obviously because we're going between 2 and 3, we'll start at 2, we'll end at 3. And the step is like how much you're going up by each time. In other words, we're going up in 0.25s in this question. If you press execute now, and then view the table, which is F6, it shows you what your ordinates are. So the x values are 2, 2.5, 2.25, 2.5, 2.75, and 3. So we can check that we've done that right. We've got 5 ordinates. And on the right, it subs into the function. So obviously, you don't need the table function. Like you could just work out what the ln of 2 is, what ln of 2.25 is. But sometimes if that function's a little bit complicated and you've got to do like loads of ordinates, it is a bit quicker if you do the table function. Just one thing to be very careful of, right? The calculator doesn't round these values. Like it just sort of truncates them. It just chops them like this. So let's see if I can find one. See that one there, 0.9162. It's not actually 0.9162. It's 0.91629. So like scroll across to get accurate values. Okay. In this question, we want to work to 3 decimal places. So we just need to make sure we're more accurate than that in our working out. All right. I'm not sure if I'm going to be able to fit this all on, but let me see. So the area would be 1/2 h, which is 0.25. And we'll do an exam question in a second. Like you want to show the method that you use in this formula, because like you want to show that you've calculated each of these y values. Don't just do it all in the calculator, because like this could potentially be worth like 5 marks. All right. So open up a bracket. Your first y value would be 0.6931. If we want to be accurate to 3 decimal places, I'll use at least 4. I'll use 5 just to be sure. So 3147, so 315. Plus, so you add your first and your last y values together. So that'd be 1.09861, and then plus. So this is all in a bracket. Apologies, I can't fit this on very neatly. You multiply the middle y values by 2, because they've counted for like 2 of our trapeziums. So it'll be 2 lots of. Okay, that's what we get. So these are the middle y values. So you've got your method marks. Essentially 1 mark probably for getting h, the marks for the y values, and then we will just use your calculator to evaluate this. Maybe don't do it all in one go. Like you might want to add these numbers up. So we could show like an intermediate step. So we've got like 1/2 times by 0.25, which is 1/8. First and last, I'm getting 1.79176. The middle values is 2.73882. And then we'll just tally this up and write our answer to 3 decimal places. So I'm getting 0.902 908,675 to 3 decimal places. 0.9086 or 909 to 3 decimal places. Okay, let's try one more question. Okay, so this is a past paper question, and we've got a sketch. We're going between the limits 1 and 2, and the equation for our curve, essentially what we're trying to do is we're trying to approximate the integral between 2 and 1 of the square root of x squared plus 1 with respect to x. Okay, luckily for us, they've given us a table straight away. So like if they give you a table like this, you can just look at it and clearly see, well, that's my first ordinate. So I'm using 1, 2, 3, 4. I'm using 5 ordinates. And the amount that we're going up by each time, like each of our strip, I could just literally say, well, h is just 0.25 in this question. But I mean, obviously, they might not give us a table, so we'd still, just to make it aware of the calculation, you'd do 2 minus 1, and then if you've got 1, 2, 3, 4, if you've got 5 ordinates, you divide by the number of strips. There's always one less, okay? And that's 0.25. So we can straight away see what h is. Okay, it just says complete the table above, given the missing value. So like, we could set it up as the table function on the calculator, but like, all you need to do now is say, well, if x is 1.25, what's our y value? And they're basically giving you a mark there. Like, so y would equal the square root, like the function that we're using is this. So 1.25 squared plus 1. Let me just work that out. 1.25 squared plus 1, and then square root. My answer. You can leave it as a third if you want, and then you won't have to worry about rounding errors, but I suppose in this question these are all to 3 decimal places. So change it into a decimal. It does say actually to 3 decimal places, so 1.6007, so be careful with that, 01 to 3 decimal places. And then 4 marks for this. Use the Trapezium rule to find an approximate value, giving your answer to 2 decimal places. So the area, part B. Again, 4 marks for this, so just set your method out. It would be 1/2 of h, which is 0.25. And then your first and your last, so 1.414 plus 2.236, and then plus, this is all in this bracket. Don't forget, so all of this stuff is being times by this number at the end. And then we do 2 lots of the middles, which would be 1.601 plus 1.803 plus 2.016. Okay, so we've got 1/8, first and last, 3.65, and then 2 lots of the middles. So if we just do 3.65 plus 2 times 5.42, and then divide all that by 8, we can see that the area is approximately equal to 1.81125 to 2 decimal places, 1.81. Okay. One thing as well, just to bear in mind, that you could actually, if you've got one of these calculators, you can get the calculator to sort of check. Remember, we're approximating this area, so there is a way of typing in the integral, isn't there? So if we type in the integral between 2 and 1, and we're doing, how do I get to that, square root of x squared plus 1. The actual, well, not the actual area, but the calculator approximates that area as 1.811009. So my approximation 1.81. You know what? We're really close, aren't we? Like, so that's what's so good about this Trapezium rule. We only split it up into a couple of strips, and it gives us like a really accurate approximation of that area. Okay. One last thing before we finish. It might ask you, is it like an overestimate? Or an underestimate? Now obviously you could work it out on the calculator and see if your one's more or less, but like you need to sort of justify your answer as well. And it's to do with the curvature of the graph. So if our graph looked like this, like imagine we were approximating this graph as a trapezium. I'm just going to draw one big trapezium just to sort of really illustrate the point. If the graph had that sort of curvature, can you see that our trapezium would be slightly more than the actual area, so that would be an overestimate. If you want to get technical, it's to do with the curvature. What's that one? It's convex, isn't it? So you could even check the second derivative, like, but I mean, if you've got time, that's a convex graph. So when it's convex, in this sort of rearrangement like this, we'll get an overestimate. For the other one, if we were trying to approximate that as a trapezium, we'd be slightly less than the area, so that would be an underestimate. And that one is concave. Because it's like a cave, isn't it? It's that I have to remember like that, but convex, concave. So it's like, that would be an underestimate. If it says justify your answer, just draw a diagram and like show that you've got like slightly more or slightly less than you needed. Alright guys, thank you.